In this video, we're going to review how you determine whether a given address you're trying to read is stored in the cache. We'll cover both direct mapped caches and set associative caches. First of all, recall our basic model of memory access. The memory is a large byte addressable array. When a program references an address from memory, the memory system delivers the contents of that address to the processor. That's a simple and very useful model, but the reality is quite a bit more complex. If all of our addressable memory actually were held on a single large device, accesses likely would be slow. Fast memory tends to be significantly more expensive than slow memory, and it would be prohibitively expensive to build a single device that contains a memory that was simultaneously very large and also provided fast access. One way to alleviate this problem is to use caching. A cache is a small, fast storage device that serves as a staging area for a subset of the data from a larger, slower memory. The contents of addresses that have been accessed recently, or which the processor thinks might be accessed soon, are copied into the cache. Subsequent accesses to those locations will be fast. Only a relatively small subset of addresses can be in the cache at a given time. Designers of cache systems work hard to try to anticipate which data should go into the cache, but it's not always possible to guess correctly which data will be accessed in the near future. An access to an address that is stored in the cache is called a cache hit and is quite fast. Access to an address not stored in the cache is called a cache miss and is much slower, both because it requires accessing the data from a slower device, but also because the block containing that data must be copied into the cache. Let's talk about how we determine whether a given address is stored in the cache. The cache is divided into a series of S sets, numbered from 0 to S-1. S is typically a power of 2. Each set contains E lines, and each line contains the contents of B consecutive memory addresses. B is also a power of 2. There is some additional data associated with each line. First, there's a valid bit, indicating whether the data in that line are reliable or not. We ignore any line for which the valid bit is 0. There is additionally a tag, which is just a fixed-length bit string. We'll see in a moment how that's used. Given an address, we need to determine if the contents of that address are currently held in the cache. To make things concrete, let's suppose that addresses in our system are 12 bits long. Our cache then must be designed for 12-bit addresses. Here's a sample address for this system. When determining whether this address is stored in the cache, we break the address into 3 fields: the tag field, the set index, and the block offset. In this case, the tag field is 4 bits, the set index is 5 bits, and the block offset is 3 bits. Our cache has parameters determined by these field sizes. For example, since our set index is 5 bits long, there are 2 to the 5th, or 32 possible values for this field. Therefore, we expect our cache to contain 32 sets. By the way, there are caches called fully associative caches that have only one set. For fully associative caches, there's no need to have any set index bits. Since the block index is 3 bits with 8 possible values, we expect each cache line to contain 8 addresses. And since the tag field is 4 bits, we expect the tag in each line also to be 4 bits long. The number of lines per set is independent of the address and is determined by the cache designer. If there's only a single line per set, it's called a direct mapped cache. If there's more than one line per set, it's called a set associative cache. The first step in determining whether the contents of an address is stored in the cache involves the set index. We use the set index bits of the address to find the appropriate set in our cache. In this case, our set index is 00001. So if the address is stored in the cache, it must be stored in set 1. In this picture, we're showing a set associative cache with 2 lines per set. Once we've found the right set, we need to determine if the address is stored in any of the lines within that set. To do that, we compare the tag field from our address with the tag fields of all of the lines in the set. If we find a line with a matching tag field and with the valid bit set to 1, then we have a hit. Recall that for our sample cache, each cache line stores the contents of 8 consecutive memory addresses in an array. The contents of our memory address is one of those. We use the 3-bit byte offset field from the address to index into the array of bytes within our line. In this case, our byte offset field is 100, or 4, so the contents of our address are at index 4 in the array. It's likely that we're accessing more than a single byte. Say we're accessing a 4-byte integer. If so, we return the 4 bytes beginning at the index position. If the integer is appropriately aligned in memory, it should all be contained within the line. We've said that 8 consecutive addresses are stored within each of our cache lines. Which addresses are they? Well, suppose we have a line in set 10 with a tag of 1001, as illustrated here. Addresses in this line will be those with tag bits 1001, set bits of 01010, that is, the 5-bit binary representation of 10, and block offset bits ranging from 000 to 111. That is, we'll get these 8 addresses. In this video, we reviewed how we determine whether an address we're trying to read is in the cache. There are many other important aspects of caching that we didn't cover, including what happens when we have a cache miss and what happens when we write to an address.